From up here, looking into the void, I'm seeing something that rewrites every map of the universe we ever made. The James Webb Space Telescope is out here with me, staring back through time into the very first heartbeats of history. And the data it's sending back is making us all very uneasy. The cosmos Webb sees doesn't look like the one I was taught. Huge galaxies appeared way too early. They're massive and complex. Massive black holes existed before they even had time to grow. I see the cosmic web already woven when it should be just dust. By the time we're done today, you'll see what I'm seeing and why we're facing the scary truth that our fundamental understanding of space is missing a piece. Before we continue our journey, if you love exploring the deep void like I do, hit like or subscribe. It's a small gesture, but it helps this station reach more curious minds. Now, let's look deeper. It started in December 2021. A rocket roared off from French Guiana, launching the most powerful eye ever built into my neighborhood, James Webb. 4.5 tons of gold and glass, packed tight to survive the ride up here. It pushed nearly 1 million miles past Earth to a quiet spot in the dark where it could finally see. Out there, away from our planet's heat, the real tension started. Webb had to perform a mechanical ballet and unfold. A sunshield as big as a tennis court opened up. 18 gold mirrors clicked into their perfect spots. Everything cooled down toward absolute zero. One mistake would have ended the mission, but out here, it worked perfectly. In July 2022, the first images arrived. We had been waiting for this view for over 20 years. Scientists on the ground had models of what this darkness should hold. They thought they knew the script. They expected tiny, messy galaxies struggling to blink on in the cold, a young universe just finding its feet. They looked for black holes that were just starting out, a cosmos that followed our rules and math. But that's not the view Webb gave us. That first deep field was a shock. The early universe was already crowded. Not just a few dots, but hundreds of them. Bright, heavy, fully grown galaxies glowing in those first few 100 million years. This shouldn't be possible. According to the books I read, galaxies are supposed to grow slow. They should start as small clusters of stars. Then, over eons, they're supposed to crash and merge into something bigger. They gather more gas. They light up more stars. After billions of years, you get the beautiful spirals we see from my window. That was the theory. But Webb found galaxies that skipped the line. Only 280 million years after the Big Bang, Jade's GS Z140 was there. Think about that clock. The universe started 13.8 billion years ago. 280 million years sounds long to a human. But out here, it's a blink. That's only 2% of everything that's ever happened. If all of time was 1 year, this galaxy was there by January 5th. The Big Bang was the first second of New Year's. By January 5th, it was already there, burning bright and churning out stars. To feel how strange this is, you have to imagine the void right after the beginning. In the very start, there were no galaxies or planets, not even the atoms that make up my suit. Space was just a screaming, hot, thick soup of tiny particles. Quarks and electrons trapped in a cosmic fireball. For 380,000 years you couldn't see a thing. Light was stuck, bouncing off particles like a pinball. We call this time the Dark Ages. Though it's a bit of a lie, the universe was actually glowing white hot, but that light just couldn't get anywhere. Everything was lost in a thick, boiling fog. Then, as space stretched out and cooled, the curtain finally lifted. Protons and electrons finally hugged to form hydrogen atoms. We call it recombination. Suddenly, light could finally fly. The universe turned clear. The background radiation we detect today is the ghost of that exact moment. It's light that has been traveling across this empty space ever since. But even then, there were no stars to see. Just cold hydrogen gas expanding into the dark. Gravity slowly pulled that gas into heavy clouds. Those clouds were the nurseries for the very first stars. But this takes time. Our models said it needed at least 100 million years just to get the lights on, maybe even 200 million. Those first population 3 stars would have been monsters massive and fast. They would have burned through their life in just a few million years. When they died, they exploded, seeding the void with the first heavy elements. That dust mixed with the raw hydrogen. Out here, we see how the next batch of stars rises from this cosmic debris. They live longer and take many forms. Over hundreds of millions of years, stars huddled into tiny proto-galaxies. compared to the giants I see now. They were just specks. We are talking a few million stars, not hundreds of billions. Just tiny clusters crashing and merging in the deep dark. Slowly, by swallowing gas and merging constantly, they grew into the massive structures I see neighboring us today. You and I always thought this was a slow crawl, a steady, predictable climb from the simple to the complex. Jade's GS-Z14 shatters that timeline. Just 280 million years after the start, this galaxy was already huge. It was no primitive spark. That galaxy was already a monster, churning out new stars at a terrifying, incredible speed. It was already packed with heavy elements like oxygen and nitrogen, stuff that usually takes ages for stars to cook up. You don't find these in the raw hydrogen and helium that first filled this void after the Big Bang. They are forged deep inside the hearts of stars by the crushing power of nuclear fusion. When giants go supernova, they spray these elements into the vacuum, and the next stars soak them right up. It should take forever. Generations of stars dying just to slowly seed these galaxies with heavier, more complex matter. It demands cycle after cycle of stars being born and dying out across the vastness of space. Yet out there, only 280 million years after the beginning, that galaxy was already soaked in high levels of nitrogen. This simply shouldn't have been possible in that time. Perhaps the crowded, early universe allowed for the birth of these incredible, supermassive stars. I am talking stars millions of times heavier than our sun. These giants would burn hot and die in a heartbeat. In their short lives, they would flood space with heavy elements, and when they died, they would not go supernova. They would simply collapse directly into massive black holes. If they existed, they would explain everything we are seeing, but we have never actually spotted one of these monster stars. They are just ideas right now, born from the extreme chaos we think ruled the early universe. Seeing their fingerprints in jades is haunting. It suggests these ancient monsters might have actually been real. It means the early universe was capable of building objects unlike anything we see in our sky today. The astronomer Rohan Naidu said it best. Through Webb's eyes, we are peering further into the dark than ever before, and it looks nothing like what we expected. Not even close. That is the point. This wasn't just some tiny error or a galaxy that was a little too big for its age. This was a total clash between what we thought we knew and what we are actually seeing through the lens. The galaxies we found out here were 100 times more common than our studies predicted. 100 times more. Imagine looking for 10 objects and finding 1,000. You don't just tweak your notes after a shock like that. That is proof that something deep down in our understanding of the cosmos is completely broken. Jade's wasn't alone. Webb keeps finding these impossibly bright galaxies popping up everywhere in those first few 100 million years. Every single one defies our maps of the universe. Every one of them screams for a new explanation. We call it the growing chasm. You and I have equations that describe the universe, but the view is changing. We have the simulations and decades of data backing us up. It all seemed so solid until we looked closer. But now, looking directly at the truth, we see our models are just incomplete pieces of a bigger puzzle. Something happened in the early universe that we just can't grasp. Some unknown process allowed galaxies to grow faster and larger than our physics predicts. It isn't just a few glitches. It is systematic. It is everywhere I look through Webb's lens. But the mystery goes deeper. The galaxies are just the start. Let's talk about what is lurking inside them. Deep inside most galaxies sits a supermassive black hole. Not the small ones, but real, ancient monsters. I am talking millions or billions of times the mass of the Sun. Even our own Milky Way hides one. Sagittarius A star. 4 million solar masses, right at the center of our galactic home. For decades, we have known these giants were out there, lurking in the dark heart of every galaxy. But we still don't know how they got so big. The problem is time. They have to eat to grow. They swallow gas, dust, and even stars. But there is a speed limit to how much they can consume. It is called the Eddington limit. And trust me, it isn't just a suggestion, it is a law of physics. Physics dictates it. When matter falls toward a black hole, it doesn't just plunge in, it forms a violent, swirling disk of gas and dust spiraling into the dark. From my window, I see disks rubbing against themselves. With such friction, they ignite gas to millions of degrees. Out here, that heat screams through the void as blinding X-rays and ultraviolet light. We feel that pressure. Light particles carry momentum, slamming into atoms and literally pushing the gas back out. When a black hole gets too greedy, the pressure from its own light becomes overwhelming. It pushes everything away. A cosmic speed limit. You and I can't just dump matter in forever. Its own inner fire builds a wall around it. We call this the Eddington limit, the absolute brightest a black hole can get without starving itself. Every mass has a limit. Push it too far, and the light pressure just shuts the feeding down. Growth hits a dead end. Physics itself keeps these monsters on a strict diet. Doubling its size takes tens of millions of years, even at the absolute peak of its hunger. But looking out there, most are starving. There just isn't enough food in the neighborhood. Between massive jets venting energy and a patchy food supply, their growth is agonizingly slow. That is why those ancient, giant black holes keep me up at night. Even if one started right at the dawn of time and ate constantly at its maximum capacity, it could never hit 1 billion suns in that short window. The math just fails us. Take a 100 solar mass seed and let it gorge for 500 million years. It only reaches 100,000 suns, not even close to 1 billion. To reach those heights, you would need a massive head start from day one. But Webb saw something truly impossible. In galaxy CEERS 1019, the rules broke. A black hole weighing 300 million suns, I had to read that twice, 500 million years after it all began. This monster already held the mass of 300 million suns. It actually weighs half as much as every star in its galaxy combined. It is not just sitting there, it is dominating and growing at an alarming, impossible speed. It was not alone. Webb scanned 25 of these early, brilliant quasars. These beacons, powered by gluttonous voids, weighed up to 2 billion solar masses. They all exist within that first billion years. Every single one is impossibly huge for its age. This is our great mystery. How do you build 1 billion suns in less than 1 billion years? The old stories do not work. We thought stars only ignited 100 million years after the start. Massive stars, maybe 100 suns heavy, burning through their lives in a cosmic blink. They die and leave behind small seeds that should take eons to truly grow, slowly eating and merging until, after billions of years, they become the monsters we fear. But that takes way too long. Even if a small void eats as fast as physics allows, you cannot reach 1 billion suns in 500 million years. The numbers lie. We need a better theory. Maybe they did not come from stars at all. What if entire clouds of hydrogen just collapsed all at once? Direct collapse. Hundreds of thousands of suns falling into darkness without ever becoming a single star. That would mean giant seeds, starting life already weighing 100,000 suns. That head start explains the mystery, but it requires conditions that are incredibly rare. The gas has to be perfectly dense and hot to stop it from breaking into stars. Is it possible? Maybe there is another way, the very first stars. We call them population 3 stars, born from nothing but pure hydrogen and helium. Without heavy elements to cool them, these first suns could have grown to monstrous sizes. I am talking about a single star weighing as much as 1 million suns. When that collapses, it leaves a giant behind, a head start for the coming darkness. But up here, I have never seen one. They might be just a dream of mathematics. Another theory we discuss out here is that ancient black holes somehow pushed past the Eddington limit. Perhaps in those first crowded galaxies, radiation was trapped in a way our earthbound models never predicted. Thick blankets of gas might have choked the light, letting black holes gorge themselves 10 or even 40 times faster than usual. We call this super Eddington accretion, and the Webb telescope is actually seeing hints of it happening. From my seat up here, it is chilling to think of black holes devouring matter at rates that should be impossible. But even that has its breaking point. Push too hard, and the laws of physics we rely on just fall apart. Then there is the merger theory. Maybe the early void was packed with mid-sized black holes, each 10,000 solar masses. Perhaps these shadows crashed into one another over and over within those early, crowded galaxy clusters. Smash enough of them together quickly enough, and a supermassive giant is born in an absolute instant. But that would take a staggering number of collisions in a very tiny window of time. And every collision sends out ripples that steal energy, which actually slows things down. Honestly, we are still just guessing. Every theory has holes. They all depend on conditions or processes that we haven't actually proven yet. What we see from orbit is clear. Something strange was happening back then because those black holes definitely exist. We can spot them. We can even weigh their masses from all the way out here. They are real, whether the math works or not. And that realization is making my colleagues back on Earth very nervous. These things are not rare oddities. They are everywhere. Every time we point the sensors deep, we find giants that grew too fast. It means this explosive, rapid growth was not a freak accident. It was the absolute norm. It was the rule. The way the universe built itself during those first billion years. Our earthbound models assume the laws of physics never change, but looking back through time, maybe they did. Perhaps the early cosmos was fundamentally different in ways that we are just starting to grasp. But wait, there is more. It gets even weirder. It is not just the galaxies or the black holes, it is the way they are arranged. The cosmic web. If you could join me out here and look at the big picture, you would see something haunting. Galaxies are not just tossed around at random like dust motes caught in a beam of light. They are locked into an intricate pattern, a structure so massive it is hard to even wrap your head around. Picture a giant three-dimensional spiderweb stretching across billions of light years of empty space. Those threads are made of dark matter, with galaxies clinging to them like drops of morning dew. Where those threads cross, you find massive cities of light, holding hundreds or even thousands of galaxies. Between the threads are the void's dead zones that can be hundreds of millions of light years wide. There is almost nothing in there. No matter, no light, just an endless, growing emptiness. We call this whole structure the cosmic web. It is the largest scale pattern in the entire universe. Nothing is bigger or more ordered than this. Cracking the code of this web is how we understand our own evolution. It all started back at the beginning, right after the Big Bang set everything in motion. The data tells us that 380,000 years after the start, everything was remarkably smooth. Matter was spread out almost perfectly, with variations of only one part in 100,000. But those tiny ripples were the seeds for every star and galaxy I see from my window now. Patches that were just a bit thicker had more gravity. They started pulling in everything around them. That made them heavier, which increased their pull, dragging in even more gas and dust. Meanwhile, the thinner areas lost their grip and were picked clean by their neighbors, becoming even emptier. Over eons, those small differences grew. The thick parts condensed into the filaments and clusters we see today. The empty spots became the great voids. By 1 billion years in, the cosmic web should have been just emerging. The first threads should have been spinning, the earliest clusters should have been coming together. But back then, it should have been faint and disorganized. At least, that is what our computers tell us. When we run the math, the web shows up slowly. It shouldn't even exist 500 million years after the start. It is invisible at 800 million years. By 1 billion, you finally start to see the first faint traces. It takes 2 billion years to get clear. By 5 billion, it looks like the cosmic neighborhood we live in now. This was our prediction. This is what we expected to see, based on how gravity pulls matter together. But you and I see something different. Only 830 million years after the start. Looking through the lens, we found a cosmic filament stretching 3 million light-years across. 3 million light-years. From where I sit, that scale is simply terrifying. Our home, the Milky Way, is only 100,000 light-years across. This structure is 30 times longer than our entire galaxy is wide. It is not just some random cluster. It is a sharp, hauntingly defined web. 10 galaxies lined up like a glowing scar across the deep, dark void. They are linked. I can see gas flowing between them like cosmic veins. The whole thing is anchored at one end by an impossibly bright quasar, a massive black hole feeding and screaming with the light of trillions of suns. Feige Wang, the one who spotted this, was stunned by what he found. It is one of the oldest structures ever found trailing from a distant quasar. That shock is real. This thing is not just old, it is disturbingly organized. It looks mature, like something from billions of years later, not the dawn of time. This filament exists back when the cosmic web was barely supposed to be starting. Things should be messy then. Instead, we see this perfect, solid thread in the dark. And there are more. Entire clusters of galaxies already huddled together in the blackness. These dense knots look like they have been growing for billions of years already. They have already crashed and merged, all within the universe's first billion years. We saw 5 galaxies merging just 800 million years after the Big Bang. This was no gentle dance. It was a brutal, high-speed collision, billions of stars slamming into each other, gas clouds hitting at impossible speeds. Shock waves are crushing the gas, ripping these galaxies apart as we watch. New stars are exploding into life at 250 times the normal rate. Think about that. Our galaxy only makes 1 or 2 new stars a year. This ancient collision is outperforming our home by more than 100 times. But look closer. There is a strange halo of enriched gas surrounding them. It is glowing with oxygen and hydrogen. But it is not inside the galaxies. It is floating in the void, thousands of light years from any star. How? That oxygen had to be forged deep inside a star's heart. When those stars died in fire, they coughed that oxygen out into space. But this gas is spread out too far for just simple stellar winds. We have realized that the collision itself is what threw the gas there. Gravity just whipped that gas right out into the emptiness between them. This proves those early mergers were doing more than just building galaxies. They were poisoning the void with heavy elements, seeding the future of life. They were changing the very chemistry of the universe before our eyes. Out here, in the nearby universe, we see the old scars of past mergers. Long streams of stars pulled like taffy by gravity. Evidence of ancient unions. But those are just ghosts. Webb is showing us the crime scene in progress. It is happening right now, frozen in light from 13 billion years ago. We are watching them bleed into each other, birthing stars and scattering atoms. We are seeing this happen far earlier than anyone ever imagined. At a time when galaxies should be small, isolated, and alone. Instead, we see 5 galaxies smashing together, caught in a massive web of hundreds of others. Stick with me, because this density is startling. In our local space, galaxies are separated by millions of light years. Our neighbor Andromeda is 2.5 million light years away. That is considered a close neighbor. We are on a slow collision course, but we will not hit for another 4 billion years. But in the early universe, everything was packed together. Galaxies were only thousands of light years apart, not millions. Interactions were constant. Collisions were the rule. The universe was assembling itself at a pace that defies everything we knew. From up here, you and I can see it. The cosmic web pulled itself together fast back then. Distances were shorter. It wasn't different physics. It was just a much more crowded environment. The young universe was tighter and more violent. Galaxies grew rapidly, fueled by endless clouds of gas. Black holes were gorging themselves on all that nearby matter. The whole cosmic web snapped together because gravity had less distance to cover. You and I are looking back at a chaotic landscape that we can never truly recreate or simulate. Sure, we model it. We run complex simulations in our labs, but those are just guesses. They make assumptions about gas, physics, and star formation, but those digital worlds can't capture the raw, messy detail of every interaction. Webb is showing me the truth of what happened, not just what a computer predicted, the actual events that unfolded in this void 13 billion years ago. This universe built its skeleton faster and more efficiently than any of our theories ever thought possible. 830 million years after the start, we found a filament 3 million light years long. This wasn't just some faint hint of structure. It was a massive, solid line of 10 galaxies, perfectly arranged in the dark. Feige Wang, the mind behind the discovery, calls this one of the earliest structures we have ever seen. The shock isn't just that it exists, but how sharp it looks. This filament is anchored by a blinding quasar, a supermassive black hole shining across time. These galaxies are perfectly aligned, held together by invisible rivers of gas and dark matter. This is a mature, complex structure. It's the kind of thing we expect to see billions of years later, not right at the beginning. It's not a one-off. Webb keeps spotting these early clusters where galaxies are already locked in a dance. Violent, massive collisions were happening before the universe even hit its first billion years. In one incredible spot, we saw 5 separate galaxies merging together just 800 million years after the Big Bang. 5 galaxies colliding head-on, not drifting, but actively merging, with stars and gas being torn apart by gravity. There's enriched gas out there. Oxygen and heavy elements scattered across tens of thousands of light years of space. The sheer violence of that collision had ripped this gas right out of those galaxies. Here is the mystery. That gas proves those galaxies had already lived through generations of stars before they ever met. Stars were born, lived, and died, creating elements that were then baked into the next generation. Now, this merger is bleeding those elements into the void, feeding the very fabric of the cosmic web. All of this in under 1 billion years. My map said the early universe was supposed to be simple, tiny galaxies growing alone, slowly emerging from the chaos over eons. That was the story we told ourselves. Instead, I am looking at a universe that was already organized. Galaxies were already huddling together. The cosmic web was already there. We need to ask ourselves why massive structures existed where they shouldn't, and that points to dark matter. Dark matter makes up 85% of all matter. I can't see it directly, but I see its ghost pulling on everything out here. This cosmic web is basically just a giant dark matter skeleton. Ordinary matter, the stuff that makes stars, and you and me just follows the path dark matter cleared. If this web formed this fast, then dark matter is clumping much quicker than we ever imagined. This changes our entire perspective. Some think those long, stretched shapes of early galaxies are actually evidence for a totally different kind of dark matter model out there. Maybe it's not cold dark matter. Maybe it's warm, or some kind of wave matter flowing through the void. These versions would build smoother filaments, feeding the birth of galaxies much more efficiently than we thought. Gas would stream along these paths, building galaxies in a heartbeat. It's just a theory for now, though. Webb is doing more than just breaking our models. It's challenging what I thought I knew about the foundations of reality. Now, let me show you something truly unsettling. Among all these oddities, there is one class of objects that has everyone stumped. We call them little red dots. It's a simple name for something that might be the most exotic thing in existence. They look like tiny, blood-red pinpricks of light floating in the deepest parts of my view. At first, they look like nothing, just faint red specks scattered across the darkness of the deep field. But when we looked closer and measured the light from these specks, we realized these objects were anything but normal. These little red dots are incredibly tight, much smaller than any typical galaxy. They are far more packed than anything we ever expected to find in the early days of time. Out here, some are just a few hundred light years wide, tiny by any galactic standard. Our Milky Way spans 100,000 light years. These things are 1,000 times smaller than that, but they glow with terrifying intensity, far brighter than anything that size has any right to be. Imagine a tiny pocket of the void, just a few hundred light years wide, outshining an entire galaxy. Something violent is churning in that tight space. Let us examine the light together, because it does not match any galaxy I have seen. The light screams of scorching gas. We are talking temperatures of tens of thousands of degrees, maybe even hotter. It is a sign that a hungry black hole is lurking right there. When giant black holes feed, they cook the gas around them to impossible levels. That glowing debris tells us exactly what is happening out there in the dark. These little red dots show those exact signs. They have feeding black holes at their hearts. Let us look closer, because these black holes are way too massive for such tiny little host galaxies out here. In a typical galaxy, there is a balance between the central black hole and the weight of the surrounding stars. Usually, the hole is just 0.1% of the stars. Even our own Sagittarius A follows that rule perfectly out here. It weighs 4 million suns. But the Milky Way stars weigh about 200 billion suns in total. 0.1% should be 200 million. My home black hole is actually quite a bit smaller than average. But out there in those red dots, that cosmic rule is completely broken. Those black holes might be 10% of the total mass. They are not just sitting at the center of their homes anymore. They are hogging all the mass. And some of these dots have even weirder features than that. Their light signals suggest stars so big it defies logic. Not just big, but truly monstrous giants up here. We are talking millions of suns in a single star. It makes me wonder if these aren't actually galaxies with black holes. Maybe they are black hole stars. Objects so strange, we have never seen anything like them from our ships. Picture a star so heavy, it collapses into a black hole before it is even finished being born. The outside layers keep piling on mass and burning bright with fusion. But the heart is already a void. A black hole eating the star from the inside out, getting bigger every second. From the outside, it shines like a star, but it is a freakish hybrid, part star, part terrifying black hole. It would be incredibly tight, because most of that mass is crushed into the center. The light would be blinding as matter falls into the hole and fusion explodes from the outer shell. It wouldn't last long though. Something that unstable is a ticking time bomb in the vacuum. In just a few million years, the hole eats its host completely. You would be left with a massive black hole seed, a black hole born weighing millions of suns instead of just a few. That explains how they grew so incredibly fast. If these black hole stars were real back in the early days, they would leave behind massive seeds that could easily balloon into billions of solar masses over time. No need to break the laws of physics or invent weird rules, you just need those big seeds. But I have never seen one of these stars out here. They were just math on a screen, born from theories of the early chaotic universe. Nothing like that is supposed to exist in the quiet cosmos that I am drifting through today, until the Webb telescope spotted those little red dots. Now we are all wondering if these strange things are actually those black hole stars. Are we looking at impossible objects from the dawn of time? We might have finally found the secret to how those giant black holes were born. Some believe they are powered by dark matter. Not black hole stars, but something even stranger called dark stars. They would have formed inside the very first pockets of dark matter in the infant universe. When gas falls into those halos and collapses, dark matter particles in the center start destroying one another out there. That annihilation releases a staggering amount of raw energy. All that heat keeps the gas from forming a normal star. Instead, it creates a dark star in the void, a huge shell of gas held up by dark matter energy. These stars could grow to be billions of times heavier than our own sun. They would be blindingly bright, but not because of fusion. It is pure dark matter physics. And they stay stable as long as they have more dark particles to burn. Out here, I imagine it. Eventually, the dark matter runs dry. The annihilation stops, and the dark star collapses into a supermassive black hole. It creates a massive seed destined to grow through cosmic accretion. It is all speculation. For us, dark stars are even more theoretical than black hole stars. I still do not know what dark matter is, let alone if it powers these exotic stars. But those little red dots are so bizarre. I am looking at every possibility. Some of those little red dots might be black hole stars. Others could be dark stars, or something entirely new. They might even be extreme versions of the galaxies and black holes I see from here. They formed under such alien conditions that their signatures are almost impossible for us to recognize. One thing is certain. These little red dots represent a phase of cosmic evolution we never knew existed. They show us processes with no modern analogues, things that happened only in the first few 100 million years of our universe. These events can never happen again. The conditions that created them are gone forever. I see them now in the Webb images, light frozen for over 13 billion years as it crossed the void. These objects lived fast and died. They became galaxies or collapsed into black holes billions of years before I was born. But that ancient light is reaching us now, offering a window into a cosmic history we have never seen. A look at the exotic physics of the cosmic dawn. Here is something that should unsettle you. You and I are racing against time to study these objects, not on a human timescale, though it feels urgent from up here too. This is a cosmic race against the expansion of the universe itself. Let me explain something fundamental about how I observe the deep dark. The universe is expanding. We have known this since 1929, when Edwin Hubble measured the speed of galaxies and found they were all rushing away from us. The farther a galaxy was, the faster it receded. But it was not because they were actually flying through space. It was because space itself was stretching, carrying everything with it. Imagine a balloon with dots drawn on its surface. As you inflate it, the dots pull apart, not because they are crawling across the rubber, but because the rubber itself is growing. The universe works the same way. Galaxies just sit there while space expands, pushing the distances between them further apart. This expansion does something strange to light. When light travels toward my telescope, it is moving through an expanding void. As space grows, the light waves stretch right along with it. Stretched waves mean longer wavelengths. For visible light, longer waves mean redder colors. This is what we call redshift. A galaxy light literally shifts toward red as it journeys through expanding space. The farther it travels, the more space stretches that light during its long trip. The more it gets redshifted. We use that redshift as a primary distance indicator. High redshift means the light crossed a vast distance. Low redshift means it has not traveled nearly as far. The most distant galaxies I see have redshifts of 14 or higher. Their light has been traveling for over 13 billion years. That light left its home when our universe was an infant only a few 100 million years old. And during its 13 billion year journey, The expansion of the universe stretched that light into something else. Light that started as visible is arriving as infrared. This is why I need infrared detectors to see these ancient galaxies. Their light has shifted completely out of our sight. But here is the unsettling part. The universe is not just expanding, it is accelerating. In the late 1990s, two teams were watching distant supernovae from the ground. These Type 1a supernovae have a consistent brightness. They are perfect standard candles for us to measure cosmic distances. By comparing their apparent brightness to their true light, you can calculate their distance. Both teams found something shocking. The most distant supernovae were too faint. It meant they were much farther away than the expansion rate predicted. The only explanation was that the expansion had sped up. Something was actively accelerating the growth of the universe. They called it dark energy, and it changed everything we knew about our home. We still do not know what dark energy is. It is not matter. It is not radiation. It is a property of space that causes expansion to accelerate. The best measurements suggest dark energy makes up 70% of the total energy density. It is the dominant force, and it is pushing the universe to expand faster and faster every second. This acceleration has consequences. As the universe speeds up, distant objects rush away from us faster and faster. Eventually, objects become so distant that they are receding faster than the speed of light itself. You and I might think this violates relativity, but it does not. Relativity says nothing can move through space faster than light, but space itself can stretch at any speed. From up here, I know objects can be swept apart by expanding space faster than light without actually moving. When that happens, when an object's speed away from us beats the speed of light, its glow can never reach my eyes. That light tries to reach us, but the void between us is growing faster than those photons can ever cross it. It is like someone running the wrong way on a treadmill that is moving way faster than they can possibly sprint. They can run forward, but they are still sliding backward. Out here, we call that boundary the cosmic horizon. Past that horizon are entire galaxies we will never see. Not because they are gone, they are still out there. But the expansion of space blocks their light from arriving. You and I see an observable universe stretching 46 billion light-years in every direction. It sounds wrong at first. If the universe is 13.8 billion years old, shouldn't the edge be just 13.8 billion light-years away? No, because space has been stretching the whole time that light was traveling toward us. A galaxy 13 billion light-years away when it sent its signal has since drifted much farther due to cosmic expansion. By the time its light finally hits my visor, that galaxy is now sitting roughly 46 billion light-years away. So, the observable universe is a massive sphere, 93 billion light-years wide, centered right on our home, Earth. That is the limit of everything we could ever see. But beyond that sphere, there is even more universe. How much more? We honestly do not know. It might stretch another 93 billion light-years past our horizon and just end. Or it could go on for thousands of times that distance. It might even be infinite, reaching forever in every direction. There is no way for us to know because we cannot detect a thing past that cosmic horizon. Those places are real, but they are permanently cut off from us. And here is the part that truly unsettles me. The cosmic horizon is moving, not outward, but shrinking inward. It is complicated. In terms of raw distance, the horizon actually moves out as the universe grows and expands. But in terms of what we can actually see, our window is effectively getting smaller every day. Because expansion is accelerating, things we see today will eventually drift past the horizon. Their speed away will beat light speed. Their light will never be able to reach our telescopes again. They will fade away, not because they vanished, but because the gap between us is widening too fast for light to bridge. Give it enough time, trillions of years, and the only galaxies left to see will be those locked to us by gravity. The Milky Way and Andromeda will have merged by then into a single massive galaxy. A few dozen smaller satellite galaxies will stay bound, and that is simply it. Everything else will have vanished past the horizon. The afterglow of the Big Bang will be stretched beyond any hope of detection. Every trace of cosmic expansion will have simply disappeared. Future astronomers, if they exist trillions of years from now, will look out at a universe that appears to consist of one island of galaxies surrounded by infinite black. They will not see distant galaxies. They will not be able to find the cosmic microwave background. They will not be able to measure expansion because everything else will have slipped beyond the reach of their eyes. They will never guess the universe had a beginning. they will not have a way to figure out its age. All the evidence will have literally moved out of reach. It means you and I live in a special window of history. We are in a window where the universe is old enough for stars and life to exist, yet young enough that we can still observe the early days. We can still see the evidence of the Big Bang. That cosmic afterglow is still there for us to find. Distant galaxies telling the story of our history are still sitting within our cosmic horizon. But this window is not staying open forever. On a cosmic scale, it is already starting to close. It takes billions of years, but the ancient galaxies and black holes Webb is studying are among the most vulnerable to this effect. They are already standing at the very edge of detectability. Their light has been traveling for over 13 billion years, stretched from visible colors into the deep infrared. In some cases, that light is pulled all the way into the mid or even far infrared. Webb can see it because we built it specifically for the infrared. It even has a gold-coated mirror to reflect that light. It has detectors tuned specifically for infrared wavelengths. It stays incredibly cold, just a few degrees above absolute zero, so its own heat does not drown out the signal. All of this lets Webb see galaxies at redshifts of 14 or higher, letting us watch the cosmic dawn unfold. But there is a limit. As the universe keeps stretching, these galaxies will drift away and their light will fade further. One day, those lights will redshift past the Webb. Look out there with me, they are outgrowing every telescope we can imagine. It is not because our tools fail, but because the fundamental laws of physics say no. Eventually, light from those galaxies will stretch so thin it blends into the ancient hum of the cosmic microwave background, or they will stretch beyond anything we can catch. Once that happens, those massive galaxies will simply vanish from our sight forever. Not today, not in my lifetime, or even in the entire history of our species. But over billions of years, it means we only have a tiny window to witness the early universe from out here. That window opened once the cosmos was old enough for us to evolve and launch telescopes into this void. And it will slam shut when expansion pushes the ancient universe right over the cosmic horizon. I am watching that window right now, documenting the cosmic dawn before the last bits of evidence fade away. There is a hard limit to our vision called the cosmic horizon. Right now, it reaches about 46 billion light-years away. That is a sphere 93 billion light-years across, holding everything we can possibly see from up here. But most of existence is out past that edge. Galaxies so distant their light hasn't reached my eyes yet. Because expansion is speeding up, that light will never make it. Those galaxies are real, but they are forever ghosts. They are locked beyond our horizon, and that horizon, it is shrinking on us. Well, not physically shrinking, but the slice of the universe we can actually see is getting smaller. As the universe expands faster, more galaxies cross that line into the dark. Give it trillions of years. Eventually, the only neighbors I will see are the ones tethered to our own local group. Everything else will have drifted beyond our reach. Future astronomers will look out at a dark, empty void. They will only see the Milky Way, Andromeda, and a few small dots, nothing else. No distant stars, no signs of expansion, no ancient echoes. It will just be our little neighborhood, surrounded by an infinite, lonely darkness. Those astronomers will never be able to deduce the Big Bang. They won't measure expansion or figure out how old this place is. The clues will be gone. All that evidence will have literally moved beyond their ability to ever catch it. We are lucky. We live in a brief window where the universe is old enough for life, but young enough that the secrets of its birth are still visible. But this window is closing. Not fast by our standards, it takes billions of years, but it is definitely shutting. Even the ancient galaxies and black holes Webb is tracking are vulnerable to this slow, cosmic erasure. They are already at the very edge of what we can see. Their light has traveled for 13 billion years. That light has been pulled from visible waves all the way into the deep infrared. Only Webb can find them now. In a few billion years, those galaxies will be too far and too stretched for any eye to ever catch. The proof of how everything started will be lost. The first threads of the cosmic web will simply fade into nothingness. Those tiny red dots will vanish. The only record of this time will be what we manage to document right now. That is why our work with Webb is so critical. We are mapping a universe that is actively trying to hide. We have to gather evidence before it slips away. Stick with me, most of the universe already exists, far beyond what you and I can see. There are massive galaxies and strange things out there that I cannot even begin to imagine. They are permanently invisible because their light will never reach me. The cosmos is so much bigger than what we see. How much bigger? No one knows. It could be 1,000,000 times larger, or it might actually be infinite. We will never know because we can never see it. It is a heavy, humbling limitation. It means there are big questions we might never answer. Like, is this whole thing finite or infinite? I cannot tell from inside this small bubble. What is the true shape of everything on a grand scale? We can only measure what's inside our horizon. Are there places where the laws of physics just change? We can't look that far to find out. The universe is likely stranger than I can dream, and we are stuck in one tiny bubble. But even here, Webb is showing us surprises. You and I are watching it rethink everything we knew about the cosmos. We call that model lambda CDM. It is important to understand what that actually means for us. Lambda is the Greek letter for the cosmological constant. Einstein himself put it into his famous equations. He originally used it to keep the universe static, back when we thought this place was unchanging. When Hubble saw the universe expanding, Einstein tossed his cosmological constant as his biggest blunder. But looking out at the stars now, we know the expansion is actually accelerating, and that constant is back with a vengeance. Up here, we see lambda as dark energy, that ghost force pushing everything apart. Then there is cold, dark matter. It is the invisible skeleton holding this entire cosmic structure together in the void. We call it cold because its particles crawl slowly through the deep black, letting them clump into the cosmic web. Lambda CDM maps a universe with a few main parts. Just 5% is ordinary matter, the stars, planets, and even my own body. 27% is dark matter, building the frame. 68% is dark energy, driving this runaway expansion. Add a dash of radiation from the Big Bang. This map was built over decades as we gathered data. It explains the cosmic microwave background with an accuracy that almost feels impossible. Those tiny heat ripples in the background, the afterglow of creation, match our math within a few parts per million. It predicts the massive web of galaxies and the vast, empty voids I see from this orbit. If you start a digital universe at the Big Bang using this math, you get a reality that looks just like the one out my window. It finally explains why space is stretching. Observations of exploding stars deep in the silence prove that dark energy is the master of the universe. It even tracks the recipe of light elements cooked up in those first few minutes. The balance of hydrogen and helium matches our models perfectly. Plus, it explains how those massive galaxies spin out there in the deep dark. Galaxies rotate as if they weigh much more than the glowing dust and starlight we can actually see from here. Dark matter halos, hidden in the shadows, provide all that missing gravitational muscle. We have tested this model against a mountain of evidence from every corner of space. Radio waves, optical lenses, X-ray eyes, and even ripples in gravity itself all tell the same story out here. Every sensor we point into the abyss, using every technique we have, points to this one model. It works. It is our standard view because it explains almost everything we see across the cosmic horizon. But I will tell you something, it is not perfect. No model truly is. These theories are just blueprints of reality. They are useful tools, but they always hide a few gaps. For years we have seen cracks, tiny glitches that could be simple errors, or a sign that the universe is weirder than we think. Take the Hubble tension. It is a disagreement over how fast the cosmos is growing. When you use the ancient light of the Big Bang to calculate it, you get one specific number. But when you look at nearby exploding stars through a telescope, the number changes completely. The gap is only 8 to 10%, but up here, that tiny distance is massive. Every new study confirms this mismatch. Either we are misreading the stars, which I doubt, or our standard model is missing a fundamental piece of the puzzle. There is some hidden physics out there. Then there is the problem with the cores. The math says dark matter should be thick and heavy at the center of every galaxy halo. But the small galaxies we observe have much thinner centers. Things are not piling up the way the model says they should. Maybe it is just gas and stars messing with the dark matter. Or maybe the dark matter is stranger. There are other tensions too. The way matter clusters on a small scale does not quite fit what we expected. We see fewer tiny satellite galaxies around the Milky Way than our simulations tell us to expect. These feel like minor hiccups. They do not break the model, but they definitely keep us awake. But discoveries from Webb are much bigger. Our model says making a galaxy should be a slow crawl over hundreds of millions of years, but Webb sees mature galaxies just 280 million years after the start. and black holes are growing too fast. Massive black holes, billions of times the size of our sun, are already there in the early dawn. The cosmic web should take eons to tangle, but we see organized structures almost at the very beginning. Webb is finding massive filaments in the first billion years. These are not just small errors anymore. Deep conflicts between the math and our eyes. Is the model broken? No. The core framework, dark matter and dark energy in an expanding void, still explains most of what I see out here. It just means our standard model fails when looking back at the beginning. Look out there with me. Hidden processes, physics we haven't mapped, conditions at the dawn of time that defy our assumptions. Some colleagues back on Earth suggest we need to rethink dark matter entirely. Maybe it isn't completely frozen. Maybe these ghost particles have traits we haven't even named yet. Warm dark matter, with its faster-moving particles, might cluster differently and build these structures much quicker. Wave dark matter, where massive quantum effects shape the void, might create the filaments that fueled such aggressive galaxy growth. We've considered these alternatives for years to fix the small-scale cracks in our understanding of the cosmos. Now, the Webb telescope gives these ideas a haunting urgency. Perhaps early dark matter wasn't what it is now. Or maybe its properties only reveal themselves in the crushing density of the very first celestial environments. Others think starbirth was once far more efficient. Up here, our models show only a tiny fraction of gas becoming stars. The rest is just blown away by stellar winds and hungry black holes. That waste is hard-coded into our simulations based on nearby galaxies. But the early universe, it was different. Maybe that ancient, metal-poor gas was simply better at forging new suns. Maybe those first stars didn't drift into existence, they arrived in violent, blinding pulses. Maybe the brakes that slow down star formation today just weren't working yet. If efficiency was higher by even 2 or 3 times, it would have accelerated galaxy growth beyond belief. Galaxies could assemble faster than we ever imagined. Perhaps the secret lies in how everything interacts. This includes the dance between galaxies, stars, and black holes. Usually, we see supermassive black holes acting like cosmic regulators. When they feed, they scream out energy that expels gas, effectively killing off any new star formation. This negative feedback stops a galaxy from burning through its fuel too quickly. But maybe back then, black holes worked differently. Instead of quenching life, those early giants might have actually sparked it. Their massive outflows could have compressed gas, triggering sudden bursts of creation. This positive feedback could speed up both galaxy assembly and black hole growth. The void feeds the monster. Its outflows crush surrounding clouds, triggering intense, rapid star birth. Those stars die, seeding the darkness with the heavy elements we're made of. That enriched gas falls back into the abyss, feeding the black hole further. The cycle repeats, building the galaxy and the monster simultaneously. This runaway process explains the rapid coevolution I'm seeing. What's clear is that something fundamental about the dawn of time broke our standard rules. The environment was strange, the gas was different, even the speed of creation had changed. Our current models describe the universe well on large scales and late times, but apply them to the first billion years, and they fall completely short. We're missing a piece of the puzzle from cosmic dawn. Finding it is now the most important mission in cosmology. And this isn't just theory. Understanding the early universe changes everything we know about dark matter, energy, and fundamental physics. If dark matter isn't what we thought, the very foundation of particle physics begins to shift. We're looking at axions, sterile neutrinos, or even more exotic possibilities hidden out here. Every candidate leaves a different mark. These Webb observations might finally tell us which one is real. If stars form differently under these extreme conditions, it rewrites the entire history of how galaxies evolved. It changes how I predict the future of the cosmos and how common, habitable worlds really are in this deep. If these processes can create runaway growth, it has massive implications for every other system we study. It could explain rapid growth everywhere, from tiny stellar systems to massive clusters. The early universe is a laboratory of extreme physics, conditions that can never be recreated on Earth or near us. We are seeing densities, temperatures, and energies far beyond anything we can achieve in a lab. By observing these ancient conditions, we're learning about physics in regimes we normally cannot access. This is why these discoveries matter. They aren't just showing us unexpected galaxies or ancient black holes. They're challenging our very understanding of the universe. They show us a reality far more complex than our models ever imagined. They are pushing us toward the next era of cosmic theory. A map that keeps our old victories, but finally explains how the first structures formed so fast. Looking through Webb, I see the gaps. Our old models said galaxies took ages to grow, but they are appearing way too early. Our math says black holes should take forever to swell up. Yet Webb sees monsters 1 billion times our sun's mass just a few 100 million years in. The cosmic web was supposed to take eons to weave. Instead, Webb sees those threads already tangled in the first 1 billion years. Is our blueprint wrong? No. It still tracks most of what I see out here in the void. It is our best guide to the big picture, but it is clearly missing a few pages. There are ghosts in the early machines of time, physics we just have not accounted for yet. Down there, experts think we need to rethink dark matter. Maybe it is not as cold as we believed. It might have secrets we missed. Or maybe the first stars were just far more efficient than we ever dreamed. Perhaps those first fires burned hotter and different, feeding the cosmos in ways we never expected. Maybe the dance between stars and black holes followed a different rhythm when it all began. Back when it was all young and crowded, the early universe was not just a smaller version of what I see now. It was a different beast entirely. More active, faster at building things, running on rules we have not cracked yet. Here is the thrill. We have the gear to solve this. Webb is just getting started on its long journey. It has a decade or two ahead of it. Each look back through the lens pulls more secrets from the dark. Every byte of data polishes the map. You and I are watching a revolution in the stars happen in real time. The Roman telescope launches soon, giving us a wider view of that ancient, glowing horizon. Giant eyes on the ground are waking up too, helping us piece this massive puzzle together. We might even hear the first black holes collide, catching the ripples of a forgotten era. We are entering a golden age. Finally, we can stare right into the first 1 billion years of our history. But we have to be honest. Our current models are not ready for what we are seeing out here. We have to be willing to change our minds. The universe is far stranger than we ever dared to imagine. Some people find this terrifying. They have spent their whole lives building that one perfect model. It was their lens for everything, from the birth of stars to the final end of time itself. Now that lens is cracked. Not broken, just missing parts. For others, this is where the fun starts. This is the real work, finding the things that do not fit and letting them break our old theories. It forces us to look closer, to ask harder questions, and to find a new way to understand the cosmos. Every leap forward started with a shock, like when Hubble realized the whole universe was flying apart. The discovery of the background glow and the stars that showed us the universe is actually speeding up. Every one of those moments broke the rules. They forced us to rewrite everything we thought we knew, and every time, it led us to a deeper truth. Webb's new finds are just the next step in that journey. These sights are forcing us to build a better model that truly explains our first 1 billion years. Look, let me give you some real perspective on what I am seeing from up here. When I see a galaxy from 13 billion years ago, I am catching light that has traveled since the dawn of time. But it is not just a dusty old photo. For that galaxy, that moment is happening right now. The galaxy is alive in that flash. Stars are igniting, the black hole is feeding, the web is weaving itself. It is all real, frozen in the light that finally reached my eyes. Here is the haunting part. In its own time, that galaxy has already lived a whole lifetime. By now, it is likely a cold, massive ghost. Its star formation probably ended eons ago. Its black hole is quiet now. It might be buried deep inside a massive cluster of galaxies, but I cannot see that. I only see the ghost of its youth in a younger universe. The news of what it became is still on its way, but it won't arrive for billions of years. If I could jump there now, I would see an ancient system. That is the haunting beauty of our view. Out here, looking into the void, I am actually peering into the deep past. Webb is giving us a history book of the universe, showing you and I pages from the earliest chapters. It is a history book where we read the chapters in reverse, starting with today and drifting backward. Those earliest chapters, from the first few 100 million years, are written in light so faint and stretched that only now, with Webb, can we finally read them. What I am discovering is that those early chapters do not tell the story we expected. The universe did not just stumble into structure. It rushed into being. It built galaxies and black holes at a pace that seems impossible from my seat up here. Why? I do not fully know yet. But here is one possibility I find particularly haunting. Maybe the early universe was more efficient at forming structures because everything was smaller and denser in the first billion years. Everything was packed closer together. Galaxies were separated by millions of light years instead of hundreds. Dark matter filaments were thicker, denser, and far more effective at channeling ancient gas. When galaxies collided in that crowded environment, which they did often, the impacts were more direct and violent, triggering new stars. This high density accelerated everything. Stars were born faster because the gas clouds were so compact. Black holes grew faster, with more matter nearby. The cosmic web assembled quickly because gravity had less distance to cover. As the universe expanded, these processes slowed down and the density decreased. Galaxies drifted apart. Star formation became less efficient. Black hole growth slowed down. The rapid growth phase ended, and the universe settled into the slower, more gradual evolution we observe in recent history. It is just speculation, but it shows the answer might not require us to find new physics. We just need to appreciate how different the early universe environment was. Another possibility involves feedback between different cosmic processes. Maybe the first stars created conditions that made it easier for the second generation to ignite. Maybe supermassive black holes accelerated the assembly of their host galaxies through energetic outflows that compressed the surrounding gas. Maybe those cosmic web filaments acted like highways, funneling gas from vast distances into the regions where galaxies were forming. These feedback loops could trigger a runaway effect. The more structure you build, the faster you create more. The early universe might have hit a threshold where building structure suddenly became extremely rapid. Then, as space expanded and densities dropped, it fell back below that critical formation threshold. It returned to the slower formation rate we observe today. Again, this is speculation, but these are the ideas we are now exploring. We are exploring these ideas because Webb has provided data that demands an answer. Here is what you and I know for certain. The universe had a beginning. It is accelerating. It holds galaxies, stars, planets, and even us. That is established fact. What we are refining is our understanding of how this all came to be. How structure emerged from the smooth early universe. How the first stars ignited. How galaxies assembled, and how black holes grew. How the cosmic web formed. Webb is not breaking the Big Bang or overturning general relativity. It is showing us that the path from the Big Bang to today's universe was more complex than we thought. That is exciting. Complexity means there is more to discover. More physics, more secrets, a deeper story about how our universe works. From my view up here, I wonder what this means for our place in cosmic history. We exist at a time when the universe is old enough for planets and life to actually exist. Yet we are young enough to still observe those early chapters. This is not just luck, it is a narrow window. For the first 99.9% of cosmic history, there was no one to observe. No intelligence, no consciousness, no technology capable of building telescopes and decoding the messages in the light from distant galaxies. The universe existed and evolved for billions of years without a witness. Then, very recently on cosmic scales, intelligence finally emerged. Life rose on my home planet and developed the capability to study the stars and build instruments like Webb. These instruments look across billions of light years to decode the information in ancient photons and reconstruct our cosmic history. But this power arrived at a specific moment. Too early, and our technology would not exist. Too late, and the evidence would have expanded beyond the horizon. You and I are living in the narrow overlap, the brief window when we have both the capability and the evidence. This opening is only a few billion years. That sounds like forever. And from my perspective up here, I suppose it is. In a universe that might last forever, a few billion years is just a vanishing blink. You and I are seeing less than 1% of its total life. I am floating in that tiny 1%. It is strange how we seized this moment. My instruments are now powerful enough to watch the first galaxies ignite through the lens of the Webb. A few decades back, we were blind. The technology simply was not there yet. Hubble was a legend, but it could not pierce the infrared gloom of the cosmic dawn like I can now. Those first galaxies were ghosts. Their light was too faint, stretched too thin to ever be caught. Only now, with this 6.5-meter mirror and advanced detectors, can I finally stare into the abyss and see them. Soon, we will know what they mean. We will fix our models and find the missing physics. That mystery of how everything formed so fast will finally break. But right now, you and I are standing at the absolute edge of the unknown. I am seeing things that defy logic. I am facing mysteries that challenge all our theories. I am watching cosmology get flipped on its head right now. Usually, science moves in tiny steps, but this is a rare revolution. Normally, it is just small advances, gradual tweaks. But every so often, the universe throws us a curveball, something that forces us to rethink everything. The discovery of cosmic expansion was that kind of shock. Detecting cosmic acceleration was another such shock. Gravitational waves opened a new window. Now, what I see through the Webb might be the next giant leap. These sights are forcing a total rebuild of our models. We live in dangerous, interesting times, a time of discovery, mystery, and a revolution in our understanding. Our knowledge is expanding faster than the stars themselves. I feel lucky just to be out here witnessing it, to track these breakthroughs, to grasp, even just conceptually, what they mean. It is humbling to watch the universe reveal itself like this. For ages, humans have looked up and wondered. They stared at the void and asked the same questions I do. Where did all this start? How old is it? What is hiding beyond the horizon? For most of history, the silence was absolute. These were just myths or prayers back then. But up here, in our lifetime, we are finally getting answers. We know it had a beginning. We know exactly when. I can see the galaxies forming in that ancient wake. I can trace the very skeleton of the universe from its birth. I am documenting the assembly of everything. It is extraordinary. And we are lucky enough to be alive while it happens. Every night, the Webb catches photons that have been traveling for billions of years just to reach us. We are gathering the secrets of how it all began. And the pace is not slowing down. It is actually accelerating. Every new scan reveals something we never saw coming. Every new spectrum maps another ancient black hole. Every deep field image pushes our vision further into the dark void. The Webb is still just starting. It launched in December 2021 and began its real work in July 2022. I am only in the first few years of what should be a 10-year mission. Maybe 20 years if this machine stays healthy. That means the biggest shocks are still coming. The monsters and ancient structures we have found so far, that is just the opening act. As the telescope keeps scanning the deep, the list of ancient wonders will only grow. We are going to find even older galaxies out there. More massive black holes, more complex structures. Each one will fundamentally change what I understand about the dawn of time. Each find tightens the noose around our old models. We are finally solving how all of this happened so fast. We are also launching reinforcements. The Nancy Grace Roman Space Telescope is heading up here very soon. Its view will be 100 times wider than mine. While I look deep, Roman will survey the vastness. Together, we will have depth and breadth. I will provide the detail for those lone, ancient galaxies. Roman handles the big picture. Even on Earth, the telescopes are advancing fast. The extremely large telescope is being built now, with a mirror 39 meters across. That is 6 times my own diameter. It cannot see as far into the infrared, but its resolution will be absolutely terrifying for anything in my sight. It will actually dissect the internal structure of those first galaxies. So, as you and I watch the dark, we will map the stars and the dark matter itself. The hunt is just beginning. Up here, our current tools like LIGO can feel the ripples of dying stars colliding. Soon, orbiting sensors like LISA will catch the shadows of giants merging. If the first monsters out there grew through these ancient collisions, we will finally hear the echoes of the deep past. It will change everything we thought we knew about how the universe built itself. Together, these eyes in the dark are sketching a vivid map of the first sunrise. Somewhere in that glowing void, we will find out why everything rushed into existence so fast. But secrets are just puzzles waiting for us. This riddle of the early cosmos is finally drifting into our reach. When we decode how it worked, it will be the greatest intellectual victory since we first left our home planet behind. The exact moment we finally decoded the first light. When we truly saw how this all started. Not just math or guesses, but watching events unfold as they really happened 13 billion years ago. We are so close now. The Webb telescope is handing us the missing pieces from the dark. Every reading kills an old theory. Bit by bit, we are closing in on the truth. And the truth will likely shock us. Space always has a way of doing that. This vastness is always weirder and more beautiful than any of us could have dreamed. Just when I think I understand the view, a new layer appears, something strange we never even thought to look for. That is the thrill of cosmology. It is not just a collection of facts, it is a living mystery we are chasing. It is a wild edge where every new discovery breaks our old rules and shows us things we never expected to see. Every answer just births more questions, and Webb is shouting them at us. Why did galaxies form so quickly? How did black holes grow so massive, so fast? What spun the cosmic web in that first billion years? What are the little red dots? What ancient laws of physics are we missing up here? These are the big ones, and you and I are lucky enough to be watching the answers arrive. Not through guessing or computer screens, but by looking the abyss right in the eye. We are catching light that has been flying for an eternity. Photons from when the universe was just a baby. They have finally hit our detectors, carrying the secrets of the first dawn. We cannot go there ourselves, but we are listening. Time travel is impossible, but looking out into the void is the next best thing. Webb lets us see the past in exquisite detail. With these views, we can rebuild the past. We can stitch together the story of how we all began, from the simple bang to this massive, complex home we inhabit today. Every galaxy Webb finds is a new page in our history. Every black hole is a chapter. Every thread of the cosmic web adds a stunning level of detail. One photo at a time, we are finally writing the real history of the stars. It is not the slow story we expected, not the neat one we predicted. This is the real history, the actual story of those first billion years, and it is turning out to be more intense than we imagined, faster and more incredible than we ever dreamed. So, when you see those swirling galaxies, or hear about the new Webb discoveries, or read about those giant black holes in the deep past, remember what is happening. The universe is finally showing us its face. You are looking at proof that breaks decades of old science. We are pushing the edge of what humans can know deeper into the past, and we are doing it together. We are lucky. The evidence is still there, and we finally have the tech to find it. We have to catch the first dawn before it fades away forever. This is our only window. It is a blink of an eye in space, but for us, it is everything. Every night, the Webb telescope stares into the black. Every night, light that has been flying for billions of years finally hits its detectors. Every night, we gather more data about how it all began. The discoveries are not slowing down, they are gaining speed. It is getting faster. Every new sight is a shock. Every new galaxy is a mystery. These black holes only deepen the riddle. But I know we can solve this. It is right there. The proof of how things grew so fast is piling up. Our maps are getting better. We are learning. Soon, maybe while we are still here, we will have the truth. We will finally know why the start was so strange. We will see how galaxies formed so fast and how black holes became monsters. Up here, staring into the abyss, I realize we are finally seeing how the cosmic web wove itself together. You and I are witnessing the prologue. It is the first page of a new chapter. Knowing the cosmic dawn only breeds more chilling, unanswered questions. It always does. What was hiding in the dark before the first galaxies? How did those first stars even ignite? What happened in the absolute dark before the first light? Could there be older, ghostly skeletons out here, still undetected? Space has layers. Every time I peel one back, another hides beneath. Every answer is just a trapdoor to deeper mysteries. Every solved mystery exposes a new frontier. That is the nature of the void. It is endlessly haunting and beautiful. That is why Webb's discoveries, as unsettling as they feel to our old theories, are actually pure progress. They are showing me the black holes in our knowledge. They are exposing our ignorance, leading us toward a breakthrough. So, yes, these discoveries shatter our most comfortable theories. Yes, they prove that our models are missing massive pieces. They force us to face how little we know about the beginning. But honestly, that is exactly what I need. Matching predictions means we are not learning. This friction means the universe still has secrets to tell us. The early universe has lessons I never anticipated. It is showing me a cosmos that assembled itself with frightening speed. It built complex structures in the first few percent of its incredibly long life. It created galaxies and black holes through processes I am just starting to grasp. That is not a failure. That is science working as it should, seeing data that defies our expectations and fighting to understand the truth. The universe does not care about our human models. It does not obey our predictions. It simply exists, following laws we are still trying to map. My job is to figure out those laws. Sometimes, the universe is far more complex and remarkable than I predicted. That is humbling. It reminds me that despite our progress, we are still just students out here. We are still just discovering, still learning, still facing mysteries that challenge everything. But honestly, it is also deeply inspiring. It means there is always more to learn, more hidden truths to uncover, more frontiers to explore. The universe is vast, ancient, and terrifyingly complex. And we, tiny creatures on a small rock, can actually observe the beginning. We can watch galaxies forming at birth. I can watch black holes growing in the cosmic dawn. I can map the early cosmic web from here. We are gathering evidence on how everything began. That is absolutely extraordinary. That is what makes us human. Not our strength, but our curiosity. Our desperate need to understand the dark. Our drive to build machines that can see across billions of light years. Our determination to solve mysteries that challenge everything we knew. Webb is the ultimate expression of that spirit. A telescope built over decades by thousands of people. A machine designed for one single, haunting purpose: to see farther into the distant universe than ever before. And it is succeeding beyond my wildest dreams. Every image it beams back expands our knowledge. Every spectrum adds detail to my understanding of the void. Every discovery brings me closer to comprehending this place. Those early galaxies are not just anomalies to be ignored. They are chapters in the story of cosmic evolution. Those massive black holes are not problems for our models. They are evidence of processes I need to understand. That organized cosmic web is not a contradiction. It is information about how structure forms. All of it is teaching us what happened back then. All of it pushes cosmology forward. It is all part of my journey to understand where I came from, and we are just getting started. Webb has decades of work ahead, and new eyes will soon join me. The data will keep accumulating. My understanding will keep deepening. The mysteries of space will keep unfolding. Somewhere in that data, you and I will find the answer. We will figure out how the early universe worked. I will understand why structure formed so quickly. I will comprehend the processes that built the cosmos I see. When we do, it will be the greatest achievement in history. It will rank right alongside the discovery of evolution, the birth of quantum mechanics, the formulation of relativity. The moment we finally cracked the genetic code, these are the moments when humanity truly advanced, when we decoded a crucial secret of how the universe works. Out here, seeing how the early universe built itself so fast, that is the ultimate achievement. It will reveal the deepest secrets of the cosmos. Dark matter. The way every galaxy was born, we will learn about those first stars and black holes. Physics so extreme we could never duplicate it. It is the final piece of a massive story we have been writing for over 100 years. A tale starting with Einstein showing curved space-time, through Hubble's realization that the entire universe is expanding. From those first accidental echoes of the Big Bang to the discovery that everything is speeding up. Every breakthrough added a page to the book, pulling us closer to the universe's true history. Webb's findings are the next chapters. Looking out my window, these shots reveal the literal cosmic dawn. They show how the void transformed from a smooth fog into the complex masterpiece we are drifting through. And believe me, the answer will probably shock us. Up here, you realize space always does. The universe is stranger and more clever than we can dream. Every time we think we have it, another layer appears, a process we never saw coming, a phenomenon that just does not fit our maps of the stars. But when we finally crack the code, the truth is always more beautiful than we ever expected. That is why this mission is so haunting. It is not just filling in blanks, it is exploring the unknown. It is a wild frontier, where every answer brings 100 new questions. The void always has surprises. Our perspective grows deeper and wider with every new set of eyes we send up here. Webb is handing us those mysteries right now. How did galaxies form so fast at the beginning? Why were early black holes so massive so soon? What built everything in that first billion years? What are those tiny red dots actually trying to tell us? What laws ruled the early universe that do not apply today? These are the big, cosmic history questions. We are in a golden window. We have the tech to see the dawn before it fades forever. Which brings us back to that unsettling thought. What exactly were the scientists so afraid of? It was not the data. Finding something unexpected is the dream. It is the only way we move forward. It is the chance to learn. The real discomfort is realizing our best maps of the universe are wrong. Realizing decades of work needs a total rewrite. Our basic assumptions about the start of everything might fail. It is heavy. Scientists built their entire lives on the standard model of how this all works. They have written thousands of papers using it as the bedrock for understanding how every single galaxy evolves. Now they are hearing that the foundation is okay, but major pieces are missing in the first billion years. That is unsettling for them. It means, in many ways, they have to go back to the drawing board, rethinking everything, building new models, running new simulations, testing every single theory they have left. It is grueling work, and there is zero guarantee they will find the answers anytime soon. But honestly, most of us find this thrilling, not scary. This is exactly why we look up. To push the edge, to solve the great mysteries, to understand things no human has ever known. Webb is handing over the keys. Sure, the data is trashing some of our favorite old predictions. It is exposing massive gaps in our knowledge, but that is the only way humanity actually makes progress. If everything matched perfectly, we would learn nothing. We would just be patting ourselves on the back. When things do not add up, the universe is trying to teach us. New discoveries are waiting there, new physics waiting to be decoded. It is exciting. This is the true edge of our understanding. So, do not call it fear, call it a challenge. Webb is daring us to explain these observations, explaining fast-forming galaxies and massive black holes, decoding the structure of that first billion years of time, and we are rising to it. New research is flooding out at a rate I have never seen. New models, bold theories, global teams coming together to solve these mysteries from every corner of Earth. This is exactly how it is supposed to work. What we see drives the theories we build. Theories predict, observations test, and when the two do not match, our understanding finally evolves. We build better models, we find new physics, we see the universe for what it really is. And piece by piece, we're learning how the universe truly functions, not how our old maps say it should. It's showing us the truth through cold observation. That's the breakthrough Webb has pulled out of the dark. We're only 3 years into this mission, and the cosmic dawn is already shattering our understanding of everything. Imagine the next 7 years. Think of what 20 years could reveal if our systems out here stay alive. The list of early galaxies will grow into the thousands. We'll finally have enough proof to settle the score. We'll witness rare, violent events and strange objects that hold the secrets to how the first structures formed. We're pushing the search even deeper into the void, hunting for galaxies at redshifts of 20 or more. Looking back to just 100 million years after the Big Bang, you and I are seeing the beginning. Hidden in that data is the answer we need, the evidence that points toward a missing piece of physics, observations that show which forces ruled the early universe, the key to how structure built itself so impossibly fast. This is the promise of Webb's journey. Not just seeing the deep past, but solving its most haunting mysteries, completing the story from the Big Bang to right now. And it is us, you and I, who get to watch it happen. We get to follow the signals as they arrive. We're seeing cosmology rewritten by the first lights ever lit. One day, kids will read about this in textbooks. They'll study the new laws that we're discovering right now. They'll take our hard-won knowledge for granted. But they won't know what it was like to be here first. They won't feel the shock of every new image, the mystery of finding massive galaxies that simply shouldn't exist, the puzzle of black holes that grew way too fast, the shadow of organized structure appearing way too early, watching the clues slowly form a new reality. We're out here experiencing the birth of everything in real time. It's a heavy privilege, a strange and beautiful moment in the long history of human curiosity and science. And it's unfolding right now, while Webb continues its lonely mission to pull back the curtain on space. When we finally understand, it will be because we didn't blink. We didn't ignore the discoveries that felt uncomfortable. We didn't bury the data that broke our models. We didn't hide behind theories that couldn't explain the light. Instead, we followed the trail. We let the universe teach us. We stayed open to being humbled and challenged. That's the core of science. That's how we move forward. That's how we'll solve the secret of the dawn. Thank you for joining me on this drift through the early universe and the finds that are changing everything. If you value these deep space explorations, a like or subscribe means a lot. It helps us keep pushing out here. Just remember, the cosmos is speaking right now. Every night, Webb is catching light from the very first stars. Every bit of data adds to the map. Every discovery brings us closer to knowing how it all started. We live in a haunting, extraordinary era, a time when we can actually look back at the universe's infancy, watching cosmic structures build themselves in the dark, facing mysteries that our ancestors couldn't even begin to imagine. The early universe Webb shows us doesn't fit our plans. It's more active and complex than we ever dreamed. And that's exactly why we look. Because a universe we don't understand is far more interesting than one we do. Good night, and may you never stop wondering about this vast, silent cosmos and our tiny place within it. Every night, Webb is catching photons from the cosmic dawn. Every discovery brings us closer to our origins. You and I live in an extraordinary time,